Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us somewhere both familiar and utterly strange, into the quantum realm. But before you settle in and get comfortable, I'd love if you could take a moment to like this video and subscribe, only if you truly enjoy these quiet explorations. And when you're ready, leave a comment to share where in the world you're listening from and what time it is in your corner of existence. There's something quietly beautiful about knowing that while we're here together, we're each experiencing this moment from our own little place in time. Now, feel free to dim the lights, maybe turn on a fan for a soft, steady hum, and let's gently begin. If your mind begins to wander, that's perfectly fine. Let it drift. We'll still be here, quietly unfolding the story. Take a slow breath and imagine, just for a moment, that you're holding something very small in your hand. So small, in fact, that you cannot see it. Not even with the most powerful microscope, something smaller than an atom, smaller than anything you have ever directly experienced. And yet, it is there, not somewhere far away in space. Not hidden deep inside a distant laboratory, but right here, forming the very fabric of your body, your thoughts, and the world around you. This is the quantum realm. It is not a place you travel to. It is not a hidden dimension behind a secret door. It is a layer of reality, always present, always active, quietly shaping everything you experience. Right now, as you listen to these words, countless tiny processes are unfolding within you. Inside your brain, signals move between cells in delicate patterns. In your chest, your heart continues its steady rhythm. In your lungs, oxygen passes into your bloodstream, carried along to nourish every part of you. And beneath all of that, beneath the chemistry, beneath the biology, there is something even more subtle, a deeper level where the rules begin to change, a level where certainty softens and possibility begins to take its place. In your everyday world, things feel solid and predictable. A cup sits on a table, a book rests in your hands, a sound travels from one place to another. Everything appears stable, continuous, reliable. But if you could gently step beneath that surface, if you could somehow look deeper, you would find a very different kind of reality. Not one made of fixed objects, but one made of patterns, of probabilities, of gentle fluctuations that never quite settle into a single definite state until something interacts with them. It is as if the universe, at its smallest scale, is not made of solid pieces, but of possibilities waiting to become real. You can imagine it like a quiet mist. From a distance, the mist looks smooth and uniform, but as you move closer, you begin to notice that it is made of countless tiny droplets, shifting and drifting, never fully still. The quantum realm is something like that, except even more subtle. Not droplets, but tendencies. Not positions, but possibilities. And somehow, from this quiet uncertainty, the entire solid world emerges. Every atom in your body, every molecule, every sensation you feel, all of it arises from this deeper layer of gentle unpredictability. Even the light reaching your eyes right now, the glow from a screen or a lamp, is shaped by quantum behavior. Tiny packets of light, called photons, move in ways that are both precise and strangely uncertain, arriving exactly where they need to be, yet never following a single, fixed path. And within your brain, as you make sense of these words, countless microscopic events are unfolding, events that rely on these same quantum rules. It is easy to imagine that your thoughts are purely abstract, something separate from the physical world, but in truth, every thought you have is supported by tiny interactions, deep within this quantum layer, there is something quietly humbling about that, to realize that your awareness, your memories, your sense of self are all connected in some distant and subtle way to processes that exist at the very edge of what we can understand. And yet, despite how strange this may sound, the quantum realm is not chaotic in the way we might expect. It is not randomness without structure. It is not disorder without meaning. Instead, it is a kind of deeper order, one that does not follow the rigid certainty of everyday objects, but instead unfolds through probabilities that are remarkably precise. If you could observe it carefully enough, you would see patterns, not fixed paths, but distributions, not definite outcomes, but tendencies that guide how events are likely to unfold. It is as if the universe is constantly balancing between many possibilities, gently leaning towards some outcomes more than others. And when something interacts with this system, when a measurement is made or a particle encounters another, the possibilities narrow, and one outcome quietly takes form. This is how the solid world emerges from something that is not entirely solid. This is how certainty grows out of uncertainty, and this is why the quantum realm feels so difficult to grasp, because it asks us to let go of the idea that everything must always be one thing, in one place, at one time. Instead, it invites us to consider a softer picture of reality, one where things can exist in a state of gentle ambiguity, where multiple possibilities can coexist, and where the act of observing or interacting plays a role in shaping what becomes real. You don't need to understand all of this at once. In fact, it's perfectly fine if it feels a little out of reach, like trying to remember a dream that is slowly fading. What matters is simply allowing the idea to settle, softly, without forcing it into something too rigid. Because as we continue, we will begin to explore these ideas one step at a time, gently unfolding the strange and beautiful principles that govern this hidden layer of reality. For now, just hold on to this quiet realization. You're not separate from the quantum realm. You're part of it. Every breath you take, every thought you have, every moment you experience is supported by processes that exist at this deep, subtle level. And as the night continues, we'll slowly begin to explore how this invisible layer gives rise to everything you know and everything you are. As that quiet sense begins to settle, that there is something beneath the surface of everyday life, something subtle and ever-present, it becomes natural to wonder where exactly this quantum realm exists. Is it hidden somewhere deep inside matter, like a secret layer tucked away beneath atoms? Or is it something more distant, perhaps a strange dimension separate from the world we know? The answer, in its own gentle way, is both simpler and more surprising than either of those ideas. The quantum realm is not a place. It doesn't sit somewhere beneath reality, waiting to be discovered like a hidden room behind a wall. Instead, it is a way that reality behaves when we look closely enough. Imagine, for a moment, watching waves on the surface of a lake. From a distance, the water appears calm and continuous, a smooth, unbroken surface stretching outward. But as you move closer, you begin to notice the subtle motion, the ripples forming, spreading, overlapping, fading. Now imagine going even deeper, beyond what your eyes can see. At some level, the water is no longer just a smooth surface, or even a collection of waves, but a vast number of tiny interactions, each one contributing to the patterns above. The quantum realm is something like that deeper level, not a separate lake beneath the lake, but the underlying behavior that gives rise to everything you see on the surface. When we say quantum, we're not pointing to a location. We're describing a set of rules, a different language that nature uses at very small scales. And in that language, things behave differently. In your everyday experience, objects feel definite. A chair is here, not there. A sound happens, and then it ends. A light turns on, and fills the room in a predictable way. But in the quantum world, this sense of certainty begins to soften. Instead of saying, "This particle is here," we begin to say something more like, "There is a certain likelihood that it will be found here, and another likelihood that it may appear somewhere else." It is not that the particle is secretly hiding in one place, waiting to be discovered. It is that, before interaction, it does not exist in a single definite location in the way we expect. Instead, it exists as a spread of possibilities, a kind of gentle cloud of potential outcomes. You might imagine it like a faint glow in a dark room. The glow is not concentrated at a single point. It is distributed softly across space. Some areas are brighter, others dimmer, but the light is not confined to one exact spot. Only when something interacts with it, when you reach out, or measure, or observe, does that glow seem to gather into a specific point. And even then, the underlying behavior has not changed. Only the way it appears to us has shifted. This is one of the most important ideas to carry with you as we move forward. The quantum realm is not hidden behind reality. It is woven into it. It is the deeper pattern that gives rise to everything we see. And because of this, the familiar world around you, the solid objects, the clear shapes, the predictable motions, can be thought of as a kind of surface layer. A stable, reliable expression of something that, at its core, is far more fluid. This does not make the world less real. If anything, it makes it more remarkable, because it means that beneath every simple moment, every ordinary experience, there is a quiet complexity unfolding. A complexity that does not announce itself loudly, but instead hums gently in the background, shaping everything without ever needing to be seen. It also helps us understand why the quantum world feels so difficult to imagine. We're used to thinking in terms of definite things, objects, positions, paths, but the quantum description replaces these with something softer. Instead of paths, we have tendencies. Instead of fixed positions, we have distributions. Instead of certainty, we have probabilities. Now, the word probability might sound like uncertainty in the everyday sense, like guessing or not knowing enough. But in the quantum world, probability is not a sign of missing information. It is part of the structure of reality itself, even if we knew everything that could possibly be known. Even if we had perfect instruments and complete knowledge, the outcomes would still unfold in terms of likelihoods rather than fixed predictions. It is as if nature, at its deepest level, does not commit to a single story until the moment that story needs to be told. Until then, multiple possibilities quietly coexist. You might picture it like a story that has not yet been written. The characters are there. The setting is prepared. The possibilities are endless. But the exact sequence of events has not yet been chosen. And when the story begins, when interaction happens, one path unfolds, while the others gently fade away. This idea may feel unusual at first, but there is something strangely comforting about it as well. It suggests that reality is not rigid and predetermined in every detail, but instead holds a kind of openness, a quiet flexibility that allows for variation, creativity, and emergence. And from this openness, everything arises, atoms form, molecules bond, stars ignite, life emerges, and eventually, awareness itself appears, able to reflect on the very processes that gave rise to it. As we continue, we will begin to explore how this behavior, this gentle interplay of possibility and outcome, leads to some of the most surprising phenomena ever discovered. we will see how something can behave like both a wave and a particle, how multiple states can exist at once, and how distant objects can remain mysteriously connected. But for now, it is enough to rest with this idea. The quantum realm is not somewhere else. It is the way reality works when we look closely enough, and you, quietly, effortlessly, are already part of it. As this softer view of reality begins to feel a little more familiar, where things are not always fixed, but instead unfold through possibilities, it becomes natural to notice something even more unusual, not just that. Things are uncertain, but that they may not even be one single kind of thing at all. In the everyday world, we're used to clear categories. Something is either one thing or another. A sound is a vibration moving through air. A pebble is a solid object you can hold. A wave spreads outward. A particle travels along a path. Each has its place. Each has its identity. But in the quantum realm, this sense of clear identity begins to blur in a way that is both subtle and deeply surprising. Imagine for a moment a tiny particle of light, something so small that it cannot be seen directly, only detected through its effects. Now, if you were to design an experiment to observe how this tiny particle moves, you might expect it to behave like a miniature object, travelling along a single path from one place to another, and sometimes it does. It arrives at a detector as if it were a small localized point, a single, precise event. But if you change the way you look at it, if you adjust the setup just slightly, something remarkable happens. Instead of behaving like a tiny object moving along one path, it begins to spread out like a wave, not confined to one route, but exploring many possible paths at once. And when these possibilities overlap, they create patterns, gentle bands of brightness and darkness, like ripples meeting on the surface of water. This is one of the most famous observations in all of physics, often illustrated through what is known as the double-slit experiment. But rather than thinking of it as a technical setup, it may be easier to imagine it in a more intuitive way. Picture a quiet pond. If you drop a single pebble into the water, it creates ripples that spread outward in smooth circular waves. Now imagine placing two small openings in a barrier, allowing those ripples to pass through. On the other side, the waves overlap, sometimes reinforcing each other, sometimes cancelling out, creating a delicate pattern of alternating lines. This is how waves behave. But here is where things become truly unusual. When tiny particles, like electrons or particles of light, are sent through a similar setup, one at a time, something unexpected occurs. Each particle arrives as a single point, and yet, over time, as many of these individual points are recorded, they begin to form the same kind of ripple pattern you would expect from waves. It is as if each particle, somehow, behaved like a wave while travelling, even though it appeared as a particle when it arrived. This is what we mean by wave-particle duality. Not that something is sometimes a wave and sometimes a particle in a simple, alternating way, but that its behaviour depends on how we interact with it. If we look for a path, it gives us a path. If we allow for possibilities, it explores them. It is not choosing between two identities. It is revealing different aspects of a deeper nature. You might imagine it like meeting someone in different settings. At work, they are focused, structured, precise. At home, they are relaxed, creative, fluid. It is the same person, and yet, the way they appear depends on the context of the interaction. In a similar way, quantum objects seem to respond to the conditions around them, not by changing what they are, but by expressing different facets of their nature. And perhaps the most intriguing part of all is this. when we try to observe both aspects at once, to force the system to reveal both its wave-like and particle-like behaviour simultaneously. It refuses. It settles into one expression or the other, as if reality itself gently resists being fully pinned down. This does not mean that observation creates something from nothing, but it does suggest that the way we interact with the system plays a role in how its behaviour becomes defined. There is a quiet partnership between the system and the act of observation. Now you might wonder, does this only apply to light, or is it something more universal? The answer is, it appears to be a fundamental feature of all matter. Electrons, atoms, even larger systems under carefully controlled conditions, all exhibit this dual nature. It is not a rare exception. It is a rule, hidden beneath the surface of everything, and yet in our everyday experience we do not notice this duality. Objects feel solid. Paths feel definite. This is because as systems grow larger and interact more with their surroundings, the delicate wave-like behaviour becomes less visible. It fades softly into the background, giving rise to the stable world we are familiar with. But it never truly disappears. It remains there, quietly, as part of the deeper structure of reality. There is something almost poetic about this idea, that everything, at its most fundamental level, carries within it a kind of dual nature, a capacity to be both localized and spread out, both definite and open, both something and a range of possibilities, and that what we perceive on is not the whole story, but a particular expression of that deeper potential. As this idea gently settles in, not as something to fully grasp all at once, but as a soft shift in perspective, we can begin to sense how it connects to the next layer of understanding. Because if something can behave like multiple possibilities at once while in motion, then perhaps it can exist in multiple states at once as well. And that is where our journey will quietly lead next. With this in mind, that something can move like a wave and yet arrive like a particle, a deeper and quieter question begins to take shape. What if something doesn't just behave in multiple ways, but actually exists in multiple states at the same time? Not one, then the other, but both, quietly, together. To explore this, let's return to something very simple. Imagine holding a coin in your hand. In your everyday experience, that coin can only be one thing at a time, heads or tails. If you place it on a table, it rests in a definite state. Even if you don't look at it, you would still assume that it is already either heads or tails, waiting to be revealed. Now imagine gently flipping that coin into the air. As it spins, it is no longer clearly heads or tails. It is in motion, a blur of possibilities. But even then, we still believe that at any given instant it must be one side or the other. We simply cannot see it clearly enough. This is where the quantum world begins to depart from our intuition. In the quantum realm, a system can exist in a state that is not simply unknown, but genuinely undecided, not hidden, not waiting to be discovered, but existing in a combination of possibilities all at once. It is as if the coin, while spinning in the air, is not secretly heads or tails at every moment, but instead exists in a delicate balance of both, not one, not the other, but a gentle blending of possibilities. This is what we call superposition. Now, it is important to approach this idea softly, because it is easy to imagine it incorrectly. Superposition does not mean that the coin is switching rapidly between heads and tails, and it does not mean that there are two coins. Instead, it means that the system is described by a range of possible outcomes, all present in a kind of quiet coexistence. You might picture it like a musical chord. When you press a single key on a piano, you hear one note, clear and distinct. But when you press several keys together, you hear a chord, a combination of notes blending into a single, richer sound. Each individual note is still part of the chord, but none of them exists in isolation. The system, as a whole, contains all of them at once. In a similar way, a quantum system in superposition contains multiple possibilities, woven together into a single unified state, and only when something interacts with it, when a measurement is made, does that gentle blend resolve into one specific outcome. It is like listening to a chord and suddenly hearing just one note emerge. Now, this may sound abstract, but it is not just a theoretical idea. It has been observed, tested, and confirmed in countless experiments, and it forms the foundation of some of the most advanced technologies we're beginning to develop. For example, in a classical computer, the smallest unit of information is a bit. A bit can be either 0 or 1, always one or the other, but in a quantum system we can create what is known as a quantum bit, often called a qubit. A qubit can exist in a state that is similar to superposition. Instead of being just 0 or just 1, it can exist in a combination of both, not switching between them, but holding both possibilities at once, until interaction brings about a definite result. To make this easier to imagine, you can think of a classical bit like a light switch. It is either off or on. A qubit, by contrast, is more like a dimmer switch. It can exist in a smooth range between off and on, blending both states in a continuous way. And when multiple qubits are combined, something remarkable begins to happen. Instead of exploring one possibility at a time, the system can explore many possibilities simultaneously. It is as if the system is gently considering multiple paths, all at once, before settling into one. This is what gives quantum systems their extraordinary potential. But beyond the technology, beyond the computation, there is something more quietly profound. Superposition suggests that reality, at its deepest level, is not fixed until interaction occurs. That before something is measured, it does not necessarily have a single, definite state. Instead, it exists as a range of possibilities, softly held together. You might think of it like a story that has not yet been fully told. The characters are there, the setting is ready, many possible paths lie ahead, but until the story unfolds, all those paths remain open, and when the story begins, one path is chosen, while the others gently fade. This does not mean that reality is random in a chaotic sense. Rather, it follows very precise patterns of probability. Certain outcomes are more likely than others. There is structure, even within uncertainty. There is order, within openness. And this balance between possibility and outcome, between openness and resolution, is one of the defining features of the quantum world. It is also deeply connected to the sense of creativity we observe in nature. From this quiet field of possibilities, new structures emerge, atoms form, molecules bond, life evolves, and perhaps even thoughts arise from patterns that were once only possibilities. There is something gently humbling in this idea that beneath every decision, every event, every moment, there exists a layer where multiple futures quietly coexist, waiting for one to take shape, and that what we experience as reality is, in some sense, the unfolding of one of those possibilities. As this idea settles in, not as something to fully resolve, but as something to gently rest with, we begin to notice another question forming. If multiple possibilities can exist within a single system, then what happens when two systems become connected? Do their possibilities remain separate, Or can they become linked in ways that stretch across space itself? And it is there, in that quiet question, that the next part of our journey begins. When we begin to see that a single system can hold multiple possibilities at once, a deeper question quietly emerges. What happens when two systems are no longer separate, not just interacting briefly, but becoming linked in a way that cannot easily be undone? In the world we are familiar with, objects are independent. If you place two coins on a table, each one has its own state. You can flip one, and the other remains unchanged. There is a clear sense of separation. But in the quantum realm, under the right conditions, this separation can soften, and something quite remarkable can occur. Two systems can become what we call entangled, and when that happens, they no longer behave as two independent things. Instead, they begin to act as a single unified system, even when they are far apart. To gently explore this idea, imagine two musical instruments, perhaps two violins. At first, they are separate. Each produces its own sound. But now imagine that they are tuned together, perfectly aligned, and played in such a way that their vibrations become deeply synchronized. So synchronized that if one string is plucked, the other begins to resonate in harmony. Not because a signal travels between them in the usual sense, but because their states are linked as part of a shared pattern. Quantum entanglement is something like this, but even more subtle. It is not simply that two systems influence each other. It is that their properties become defined only in relation to one another. For example, imagine creating a pair of particles in such a way that their properties are connected. If one particle is later found to have a certain value, the other will be found to have a corresponding value instantly, no matter how far apart they are. You could carry one particle across a room, or across a continent, or even imagine sending it far into space, and still, when you observe one, the other responds in perfect correlation. This is not a signal travelling through space in the usual way. It is not something moving from one point to another. Rather, it's a reflection of the fact that the two particles were never truly separate to begin with. They are part of a single, shared description, a single system expressed in two places. This idea was once so surprising that even some of the greatest physicists found it difficult to accept. Albert Einstein, for example, referred to it as spooky action at a distance, not because it was mystical, but because it seemed to challenge our deeply held assumptions about how the world should work, and yet over time careful experiments have confirmed that this phenomenon is real. When scientists create entangled pairs and measure their properties, the correlations they observe cannot be explained by any simple hidden mechanism. It is not that the particles secretly agreed on their values in advance. It is that their properties do not fully exist in a definite way until they are observed. And when they are, they appear in a coordinated pattern. You might imagine it like 2 pages of a book that were once part of the same story. If you read one page and find a certain sentence, you already know what will be written on the other page, not because information travelled between them in that moment, but because they were always part of the same narrative. In a similar way, entangled particles share a deeper connection, one that is not bound by distance in the way we usually think. And what makes this even more fascinating is that entanglement is not limited to separate particles floating through space. It also appears within the very structure of matter itself, inside each atom, inside the tiny building blocks that make up everything you see. There are particles whose behaviours are deeply interconnected. Even within a single proton, the small positively charged component at the centre of an atom, the particles inside are linked in ways that reflect this same underlying principle. This means that entanglement is not something rare or exotic. It is part of the fabric of reality, quietly present, even when we are not aware of it. And as we have learned to work with this phenomenon, it has begun to open new possibilities. For example, scientists have developed ways to use entanglement for communication systems that are extraordinarily secure. In these systems, information is encoded in delicate quantum states, and because any attempt to observe or interfere with those states changes them, it becomes immediately clear if someone is trying to intercept the message. It is as if the message carries within it a kind of awareness, revealing any disturbance. This does not allow faster-than-light communication, but it does allow a new level of trust, grounded in the fundamental behavior of nature itself. There are also experiments that have extended entanglement across vast distances. Pairs of particles have been linked across hundreds of kilometers, even between ground stations and satellites. And still, the correlations remain quiet, consistent, reliable. All of this suggests something profound, that the separations we perceive, the distances we measure, may not fully capture the deeper connections that exist beneath the surface, that at a fundamental level, reality may be less like a collection of isolated objects, and more like a single, interconnected system, gently expressing itself in many places at once. There is something both humbling and comforting in that idea, that beneath the appearance of separation, there may be a quiet unity, a subtle thread connecting things that seem apart. As this thought settles, not as something to fully resolve, but as something to gently consider, another question begins to take shape. If systems can become so deeply connected across space, then what limits our ability to know them completely? Why can we not simply measure everything precisely, all at once? And it is there, in that gentle limit, that we begin to encounter another fundamental feature of the quantum world, one that does not arise from our lack of knowledge, but from the very nature of reality itself. As this connection gently comes into view, suggesting that things may be linked in unseen ways, another subtle idea begins to unfold, not about connection this time, but about limits, a gentle boundary woven into the fabric of reality itself. In the world we experience each day, it feels natural to assume that if we look closely enough, measure carefully enough, we could, in principle, know everything about something, where it is, how fast it is moving, where it came from, and where it is going. With enough precision, enough care, enough patience, it seems like the universe should reveal all of its details. But in the quantum realm, this expectation begins to soften, not because our tools are imperfect, not because we lack skill or knowledge, but because there is a fundamental limit built into reality itself. This idea is known as the uncertainty principle, and despite its name, it is not about confusion or ignorance. It is not about failing to measure accurately. It is about the fact that certain property cannot both be known with complete precision at the same time. To explore this gently, imagine trying to observe a small object moving through a dimly lit room. If you focus on its position, where it is at a particular moment, you might use a bright flash of light to illuminate it clearly. For that instant, you see exactly where it is. But that flash of light also disturbs the object, nudging it slightly, altering its motion. Now, if you try instead to track how it is moving, its direction and speed, you might use a softer light, observing it over time. In doing so, you gain a better sense of its motion, but lose some precision about its exact position at any single moment. In this everyday analogy, the limitation comes from the act of observation, but in the quantum world the situation runs deeper. Even if we imagined a perfectly gentle observation, one that caused no disturbance at all, the limitation would remain, because it is not just about how we measure. It's about how reality is structured. At its most fundamental level, there is a balance between certain pairs of properties. For example, position, where something is, and momentum, how it is moving, including both its speed and its direction. The more precisely one of these is defined, the less precisely the other can be defined, not hidden, not waiting to be revealed, but genuinely undefined, beyond a certain level of clarity. You might imagine it like trying to describe a musical note that is both perfectly sharp in pitch and perfectly brief in time. If the note is extremely precise in pitch, pure and steady, it must last for a longer duration. If it is extremely brief, just a quick tap, it spreads out in pitch, becoming less precisely defined. There is a natural trade-off, not because of limitation in your hearing, but because of the nature of sound itself. In a similar way, quantum systems carry a built-in softness, a gentle blur that prevents everything from being pinned down all at once. And rather than being a flaw, this softness is essential. Without it, atoms could not exist in stable forms. Electrons would collapse into the center of atoms, unable to maintain the delicate balance that allows matter to have structure. The world would lose its richness, its variety, its ability to form complex patterns. In a sense, uncertainty is what allows existence to have space, both literally and metaphorically. It creates room for structure to emerge, for systems to stabilize, for interactions to unfold. It is not chaos. It is not randomness without meaning. It is a carefully balanced openness, a built-in flexibility that supports the complexity we observe in the universe. You might think of it like the softness in a piece of fabric. If the fabric were completely rigid, it would tear under pressure. But because it has some flexibility, some give, it can bend, stretch, and hold together. Uncertainty provides that flexibility at the deepest level of reality. Now, it is important to approach this idea gently, because it can be tempting to imagine uncertainty as something mysterious or unpredictable in a dramatic way. But in practice, the patterns of uncertainty are highly structured. They follow precise mathematical relationships, even if we do not express them in symbols here. Scientists can predict, with remarkable accuracy, how likely different outcomes are, even when exact values cannot be fixed simultaneously. There's order within the blur, a quiet, reliable pattern beneath the softness, and this pattern allows us to understand, design, and interact with quantum systems in meaningful ways. It is what makes technologies like quantum sensors possible, allowing us to detect incredibly small changes in motion, gravity, or energy. By working within these natural limits, it is also part of what shapes the behavior of particles, guiding how they move, interact, and form the structures we depend on. There is something deeply reassuring about this, that even at the most subtle level, where things are not fully definite, there is still a kind of harmony, a balance, a quiet consistency that holds everything together. As this idea gently settles, we begin to see the quantum world not as something chaotic or unpredictable, but as something finely tuned, a place where limits are not barriers, but conditions that allow beauty and complexity to arise. And as we continue, another question begins to form. If reality carries this softness, this openness, this ability to exist in multiple possibilities, and this limit to how precisely it can be defined, then what happens when we look even closer? Do these strange behaviors remain consistent, or do they begin to take on forms that challenge our intuition even further? It is there, just beyond this gentle boundary, that the next layer of our journey begins. Time equals 3 seconds / greater than. As these ideas begin to settle, that reality is not always fixed, that things can exist in multiple possibilities, and that even our ability to know them has gentle limits, something even more curious begins to emerge. Not about where things are, not about how they move, but about what they are. In the world we're used to, objects and their properties feel inseparable. A cup has a shape, a sound has a tone, a moving object has a position and a direction. These qualities belong to the object, they travel with it, they define it. It would feel strange, almost impossible, to imagine separating a property from the thing that carries it. And yet, in the quantum realm, something like this appears to happen. To explore this gently, let's begin with a familiar image. You might remember a character from a story, a cat that could slowly disappear, leaving behind only its smile, a floating grin. Without the cat itself, it is a playful idea, a bit surreal, the kind of thing we associate with imagination rather than reality. But in certain quantum experiments, something surprisingly similar has been observed. Not with cats, of course, but with tiny quantum systems. In these experiments, scientists carefully prepare a system so that different aspects of it can take different paths. For example, a particle may be arranged so that its presence, its location, follows one path, while one of its properties, such as its orientation or spin, follows another. Now, rather than thinking in terms of technical details, you can imagine it like this. Picture a small object travelling through a fork in a path. In one direction, the object itself moves forward. In the other direction, a certain quality of that object seems to travel instead, as if the object and one of its defining characteristics have gently parted ways, not completely disconnected, but no longer fully bound together in the way we expect. This phenomenon is sometimes described as the quantum Cheshire cat effect, not because there is anything mystical about it, but because it reflects a similar idea, a property appearing where the object itself is not. Now, it is important to approach this carefully. We're not saying that an object literally splits into pieces, nor are we saying that properties float freely like independent objects. Rather, what is happening is more subtle. In the quantum description of a system, what we call an object is not always a simple, indivisible entity. Instead, it is described by a set of possibilities, a structured pattern that includes both where it might be and what properties it might have. Under certain conditions, these aspects can be arranged in such a way that they appear to follow different paths when measured. It is not that the property has left the object. It is that our classical idea of object plus property is too rigid to fully describe what is happening. In a sense, the quantum system is not a solid thing carrying fixed attributes. It is more like a pattern, a relationship, a distribution of possibilities that can express itself in different ways depending on how we interact with it. You might imagine it like a melody. A melody has pitch, rhythm, and tone. But if you listen closely, you can focus on one aspect at a time. You might follow the rhythm, while the pitch fades into the background, or notice the tone, while the structure of the melody becomes less distinct. The melody itself has not been split, but your interaction with it highlights different aspects, almost as if they were moving separately. In the quantum world, something like this happens at a much deeper level. The object is not a tiny solid piece, but a set of relationships, and those relationships can be expressed in ways that challenge our usual expectations. And what makes this even more intriguing is that these effects are not just theoretical. They have been observed in carefully designed experiments, where scientists can track different aspects of a quantum system and show that they behave as if they're taking different paths. Again, not literally separating, but behaving in a way that cannot be explained by the classical picture of an object carrying all its properties together. This invites us to reconsider something very basic. What do we mean when we say that something exists? Do we mean a solid object, located in one place, with clearly defined properties? Or do we mean something more subtle, a system of possibilities, where location and properties are not always bound in the way we expect? The quantum realm seems to suggest the latter, that at its deepest level, reality is not made of simple building blocks, but of patterns, relationships, and potential expressions that only take on definite form through interaction. There is something quietly profound in this, because it suggests that the way we divide the world into objects and their attributes, into things and their properties, may be a useful approximation, but not the full story. It is like looking at a painting and focusing only on individual brush strokes. Each stroke is real, but the meaning of the painting emerges from how they relate to each other, how they form patterns, how they come together. In the same way, quantum systems seem to resist being reduced to isolated pieces. They invite us to see reality as something more interconnected, more fluid, more relational, and as this idea gently settles, not as something to fully resolve, but as something to quietly reflect on, another question begins to take shape. If properties and objects are not always tightly bound, if the structure of reality is more flexible than we imagined, then perhaps even the boundary between the very small and the larger world we experience is not as clear as it seems. Perhaps the strange behaviors we associate with tiny particles do not simply vanish as things become larger. Perhaps they remain hidden, softened, but still present, and it is there, at that boundary, that our next step unfolds. As this softer understanding begins to take shape, that objects are not always as solid or self-contained as they seem, another question begins to form almost naturally. If the quantum world behaves this way, fluid, interconnected, gently undefined, then where does it end? At what point does reality become stable, fixed, predictable? Is there a clear boundary, a line that separates the strange behavior of the very small from the familiar world we live in? Or is that boundary more like a gradual transition, something that fades rather than suddenly stops? To explore this, let's begin with something intuitive. In your everyday experience, larger objects feel stable. A table does not exist in multiple places at once. A glass does not shift between possibilities. A book does not spread out like a wave. Everything appears definite, solid, reliable. And for a long time it was assumed that quantum behavior was limited to the smallest scales, tiny particles, atoms, light. But as experiments became more precise, something unexpected began to emerge. Under carefully controlled conditions, larger and larger systems began to show signs of quantum behavior, not just individual particles, but collections of particles acting together. Imagine a tiny mechanical object, something so small it is almost invisible, but still made up of trillions of atoms. Now imagine that this object is placed into a state where it is both vibrating and not vibrating at the same time, not switching between the two, not uncertain in the everyday sense, but genuinely existing in a combination of both possibilities, much like the coin we imagined earlier. This is not a thought experiment, it is something that has been achieved in laboratories, systems containing vast numbers of atoms, arranged in such a way that they behave as a single quantum entity, a single system, holding multiple possibilities at once. And as researchers continue to refine these experiments, the scale continues to grow. Tiny beams of material, small enough to be seen under a microscope, have been entangled with one another. When one moves, the other responds, not through a visible signal, but through a shared quantum state. It is as if two objects, each made of countless particles, begin to act as one, not metaphorically but physically, measurably, consistently. This invites a quiet reconsideration of something we often take for granted. The idea that size determines behaviour, that small things are strange and large things are stable, but the quantum world suggests something more nuanced. It is not size alone that determines behaviour, it is interaction. When a system is isolated, protected from disturbances, it can maintain its delicate quantum nature even as it grows larger, but as it interacts with its environment, as it exchanges energy, as it becomes entangled with countless surrounding influences, that delicate behaviour begins to soften, not disappear entirely, but fade into the background. You might imagine it like a ripple in still water. If the water is perfectly calm, the ripple can travel far, maintaining its shape. But if the surface is disturbed, filled with overlapping waves, the ripple quickly blends into the noise. It is still there, but no longer clearly visible. In a similar way, quantum behaviour is most noticeable when systems are quiet, isolated, shielded from external influence. And as systems become larger, they naturally interact more with their surroundings. Air molecules, thermal energy, electromagnetic fluctuations all contribute to a kind of background noise that gently washes out the delicate quantum patterns. This is why the world around you appears stable, not because quantum behaviour has stopped, but because it has been softened, averaged out, woven into a larger, more consistent picture, and yet it never fully disappears, even in the most ordinary objects. The underlying quantum structure remains quiet, subtle, foundational. There is something quietly profound in this, that the solid world you experience is not separate from the quantum world, but an expression of it at a different scale, a kind of emergent stability arising from countless tiny interactions. You might think of it like a crowd of people. Each individual is moving, shifting, making small, unpredictable choices, but from a distance, the crowd appears to flow smoothly, almost like a single unified movement. The individual variations are still there, but they blend into a larger pattern. In the same way, the classical world, the world of solid objects and definite positions, emerges from the collective behaviour of countless quantum systems. And this brings us back to the question, where does the quantum world end? Perhaps it does not end at all. Perhaps it is always present, underlying everything, expressing itself more clearly at small scales and more subtly at larger ones. Not a boundary, but a gradient, a gentle shift from possibility to stability, from openness to definition. And as we begin to see it this way, another realization begins to form. If the difference between quantum and classical is not absolute, if it is shaped by interaction, by environment, by the quiet blending of possibilities, then there must be a process, a mechanism that guides this transition, a way in which the delicate patterns of the quantum world become the stable structures of everyday life. And it is there, in that quiet transformation, that the next step of our journey begins. As this question begins to settle, where the quantum world does not seem to end, but instead fades gently into the world we experience, it leads us to something deeply important, a quiet process, almost invisible, that shapes how reality appears to us. Because if the quantum world is always present, if even large objects are built from these subtle possibilities, then why does everything feel so stable? Why does a chair remain in one place, instead of spreading out across many? Why does a glass sit calmly on a table, instead of existing in multiple states at once? The answer lies in a process known as decoherence, but rather than thinking of it as something complex or abstract, it may be easier to approach it in a softer way. Imagine once again a still body of water. If you drop a single pebble into it, gentle ripples spread outward, clear, smooth, and easy to follow. The pattern is visible, the motion is coherent, unified. Now imagine that the surface of the water is no longer still. Wind begins to blow, other ripples form, waves overlap, intersect, interfere with one another. The original ripple is still there, in a sense, but it becomes difficult to distinguish. It blends into the surrounding motion, losing its clear identity. This is similar to what happens in the quantum world. A small, isolated system, like a single particle or a carefully controlled object, can maintain its delicate state of superposition. Its ripples of possibility remain clear, but as soon as it begins to interact with its environment, even in the slightest way, something changes. The system becomes entangled, not just with one or two other particles, but with countless elements of its surroundings. Air molecules, thermal energy, light, electromagnetic fields. All of these interactions begin to overlap, and as they do, the clean, delicate pattern of superposition becomes harder to maintain. It does not disappear completely, but it spreads out, becoming entangled with so many external influences that its original coherence is no longer visible in a simple way. This is decoherence, a gentle fading, not a sudden collapse, a blending into the background of the larger world. You might imagine it like a whisper in a quiet room. When the room is still, the whisper is clear, but as more sounds enter the space, conversations, footsteps, distant noise, the whisper becomes harder to hear. It is still there, but no longer distinct. In the same way, quantum systems lose their whisper-like coherence as they interact with the environment, and as a result, they begin to behave in ways that appear classical, definite, stable, localized. This is why the world around you feels solid, not because quantum behavior has stopped, but because it has been woven into a much larger system, where its delicate patterns are no longer individually visible. There is something quietly beautiful about this idea, that the stability of your everyday world, the reliability of objects, the predictability of motion, all arise from a deeper layer that is constantly shifting, constantly interacting, constantly blending. It is not that the quantum world is replaced, it is that it becomes part of a larger harmony. Now, one of the most important things to understand is that decoherence does not require a conscious observer. It does not depend on someone looking or measuring in a deliberate way. Interaction itself is enough. Any exchange of energy, any contact with the surrounding environment, contributes to this process. This helps clarify something that can often feel confusing. Earlier, we explored how observation seems to play a role in shaping outcomes. But here, we begin to see that it is not awareness alone that matters. It is interaction. The moment a system becomes connected with its environment, its range of possibilities begins to narrow, not because it is being watched, but because it is becoming part of a larger system. And within that larger system, certain outcomes become more stable than others, more reinforced, more consistent. This is how definite reality emerges. not as a sudden event, but as a gradual process, a quiet transition from possibility into stability, from superposition into what we experience as a single outcome. And yet, even as this transition occurs, the underlying quantum structure remains, hidden but still present, like the individual voices within a choir. When you listen to the full harmony, you hear a unified sound, but within that sound, each voice still exists, contributing to the whole. In the same way, the classical world is not separate from the quantum world. It is a kind of collective expression, shaped by countless interactions, guided by deeper patterns. This perspective also helps us understand why it's so difficult to observe quantum effects directly in everyday objects. It is not that they are absent, it is that they are overwhelmed by interaction. To observe quantum behavior clearly, scientists must carefully isolate systems, cool them, shield them, protect them from external influence, creating conditions where coherence can be preserved. And under those conditions, the strange, beautiful behavior of the quantum world becomes visible again. There is something gently poetic in this, that the deeper nature of reality is not hidden because it is far away, but because it is too delicate to remain visible in a world full of interaction. And as we begin to see this, another realization begins to form. If the classical world emerges from quantum interactions, if stability arises from deeper patterns, then perhaps the rules we have learned so far are not fixed boundaries, but part of a larger evolving understanding. Because even now, scientists continue to explore new states of matter, new forms of behavior that challenge what we thought we knew, and it is there, in these new discoveries, that our journey quietly continues. As this understanding gradually takes shape, that the world we experience emerges from deeper layers, and that even the boundary between the quantum and the classical is not fixed, it becomes natural to ask something a little more subtle. If the rules of the quantum world are already so different from what we expect, are the categories we use to describe it truly complete? Or are they, like many of our ideas, only temporary ways of organizing something far more flexible? For a long time, physicists believed they had a fairly clear picture of the basic types of particles that exist, not individual particles like atoms or molecules, but the deeper categories that describe how these tiny building blocks behave. Two of the most important categories are often described in simple terms as particles that prefer to stay apart and particles that are comfortable sharing the same state. The first group includes things like electrons, which resist being in the same configuration as one another. The second group includes particles of light, which can gather together in large numbers, behaving in a more collective way. These categories have helped us understand a vast range of phenomena, from the structure of atoms, to the behavior of light, to the formation of matter itself. They are not arbitrary. They reflect deep patterns in the way nature behaves. And yet, as experiments have become more refined, as we've learned to create new materials and explore new conditions, something unexpected has begun to appear. Particles, or more precisely particle-like excitations, that do not fit neatly into either category. Not fully one, not fully the other, but something in between. You might imagine it like meeting someone who does not fit into familiar personality labels. Not simply quiet, not simply outgoing, but someone who expresses both qualities in different contexts without contradiction. At first, it might seem confusing. We like categories because they help us make sense of the world. They create order. They provide clarity. But nature, it seems, is not always concerned with our need for neat definitions. In certain carefully prepared systems, often involving complex materials at very low temperatures, scientists have observed what are known as fractional excitations. Rather than behaving like whole, indivisible units, these excitations appear to carry portions of properties we once thought were fundamental. It is as if something that we believed could not be divided begins to reveal a more subtle structure, not breaking apart in the usual sense, but expressing itself in new, unexpected ways. To approach this gently, you might imagine a wave moving through a crowd. The wave itself is not a single person. It is a pattern, a collective motion, passing through many individuals. Now imagine that this wave begins to behave as if it has its own identity, its own properties, even though it is not a single object. This is similar to how these new quantum excitations behave. They are not particles in the traditional sense. They are patterns within a system, patterns that can move, interact and carry properties, almost as if they were independent, and in some cases, these patterns behave in ways that blur the distinction between our established categories. They are not confined to being one type or another. They exist comfortably in between. This tells us something important, that the categories we use, useful as they are not the final word. They're tools, ways of describing patterns we've observed so far. But as we look deeper and create new conditions, new forms of behavior begin to emerge. It is as if the universe is gently reminding us that our understanding is always evolving. There is something quietly beautiful in that even in a field as deeply explored as quantum physics, there is still room for surprise, still room for discovery, still room for new ways of thinking. And these discoveries are not just abstract. They have real implications, new kinds of materials, with unusual electrical properties, with the ability to conduct energy in unexpected ways, with resilience under extreme conditions. All of these are being explored through these new forms of quantum behavior. In some cases, these materials can support states where energy flows with almost no resistance. In others, they reveal entirely new ways for particles to organize themselves, forming structures that do not resemble anything in the classical world. And as we continue to study these systems, we begin to see that the quantum realm is not static. It is not a fixed set of rules that we simply uncover and then fully understand. It is a living framework, one that continues to reveal new layers as our ability to explore. It deepens. You might think of it like exploring a vast landscape. At first, you map the major features, mountains, rivers, valleys. You begin to understand the general structure, but as you move closer, as you explore more carefully, you begin to notice smaller details, hidden paths, subtle variations, new formations that were not visible from a distance, and sometimes entirely new regions that reshape your understanding of the whole. In the same way, quantum physics continues to expand, not replacing what we have learned, but enriching it, deepening it, adding new dimensions to our understanding. And as this idea gently settles, that even the most fundamental categories may be more fluid than we once believed, it opens the door to something even more expansive. Because if particles can behave in new ways, if patterns can emerge that challenge our expectations, then perhaps the very states of matter themselves, the ways in which energy and structure organize, may also be more diverse than we imagined. And it is there, in these new forms of matter, that our journey quietly continues. As this perspective gently takes shape, that even the categories we use to describe particles are not fixed, it begins to open the door to something even broader, not just new kinds of particles, but new ways that matter itself can exist. In your everyday experience, matter feels familiar. You know the basic forms, a solid, like a table or a stone, holding its shape, a liquid, like water, flowing and adapting to its container, a gas, like air, spreading freely through space. These categories are so deeply ingrained that they feel complete, as if they describe everything that matter can be. But as we move deeper into the quantum world, this picture begins to expand, because at very small scales and under carefully controlled conditions, matter can organize itself in ways that do not fit neatly into these familiar categories. Not quite solid, not quite liquid, not quite anything we encounter in everyday life. To gently approach this, imagine a group of dancers moving together. In one arrangement, they stand still, each holding a fixed position. This is like a solid. In another, they move fluidly, flowing past one another. This is like a liquid. And in another, they move freely and independently, spreading out across a space. This is like a gas. But now imagine something more unusual. The dancers are still moving, but their movements are deeply coordinated. They form patterns that shift and flow, yet remain structured. They are not locked in place, and not completely free. They exist somewhere in between. This is closer to what we find in certain quantum states of matter. One example involves something known as excitons. Rather than thinking of them as particles in the usual sense, you can imagine them as pairs, a kind of delicate partnership formed within a material. When energy enters a system, such as when light interacts with certain materials, it can create a situation where a negatively charged component and a positively charged absence move together as a bound pair. Not separate, not independent, but linked in a way that allows them to move through the material as a single coordinated entity. Now, when many of these pairs form together, something remarkable can happen. They can begin to behave collectively, creating what is sometimes described as a kind of quantum liquid. Not a liquid in the everyday sense, but a state where these pairs flow together, maintaining a shared structure. It is as if the material develops an internal rhythm, a coordinated motion that does not fit into the usual categories of matter. There are also materials where electrons, the tiny carriers of energy, organize themselves into patterns that resemble waves, or even crystalline structures, not of atoms, but of motion itself. In these systems, what defines the state is not just where the particles are, but how they move together, how they relate to one another, how their collective behavior creates something new. You might think of it like a crowd at a concert. Individually, each person is simply standing or moving, but when the crowd begins to sway together, to move in rhythm, a new pattern emerges, a kind of collective motion that cannot be reduced to any single individual. In quantum materials, similar collective patterns arise, and these patterns can have unusual properties. For example, in some systems, electrical resistance, the tendency of a material to oppose the flow of energy, can drop dramatically. Energy can move through the system with very little loss, almost as if the material has found a more efficient way to carry motion. In other cases, materials can become remarkably stable under extreme conditions, resisting disturbances, maintaining their structure. Even in environments where ordinary materials would fail, there are also states where matter behaves like a kind of hybrid, partly ordered, partly fluid, exhibiting characteristics that seem to belong to multiple categories at once. These are sometimes described as quantum liquid crystals, states that exist at the boundary between different phases, again, not fitting neatly into any single description. All of this points to something important, that matter is not limited to the forms we encounter in everyday life. Those forms are simply the most stable, the most common, the most visible under ordinary conditions, but beneath them there is a much richer landscape, a range of possibilities shaped by the interactions between particles, by temperature, by energy, by the environment, and as we learn to control these conditions more precisely, we begin to uncover new regions of that landscape, new ways for matter to organize itself, new patterns of behavior, new properties that can be harnessed, not just for understanding, but for practical use. You might imagine it like discovering new colors, beyond the ones you have always known. At first, it feels surprising, even difficult to name. But over time, these new colors become part of your palette, expanding what you can create, what you can imagine. In the same way, these new quantum phases expand our understanding of what matter can be. They remind us that the world is not limited to what we're used to seeing, that beneath the familiar, there are layers of possibility waiting to be explored. And as this idea gently settles, another realization begins to take shape. If matter can exist in new forms, if particles can organize in unexpected ways, then perhaps the same is true for something even more abstract. Not matter, but information. The patterns that describe systems, the relationships that define what is possible. What if information itself can take on different states? What if it can transform, shift, reorganize in ways that resemble the changes we see in matter? And it is there, in this quiet question, that our journey continues. As this sense of expansion continues to unfold, revealing that matter itself can take on new forms, new patterns, new ways of organizing, it invites a deeper and more subtle question. If matter can change its state, what about information? Not the kind of information you read on a screen or hear in a conversation, but the deeper kind, the patterns that describe how things exist, the relationships between parts of a system, the hidden structure that determines what is possible and what is not. In our everyday thinking, information feels abstract, something separate from the physical world, a description, not a substance. But in the quantum realm, this distinction begins to soften, because information is not just something we use to describe reality, it is woven into reality itself. To explore this gently, imagine a simple example. Think of a message written on a piece of paper. The words carry meaning, but they're also tied to a physical form, the ink, the paper, the arrangement of symbols. Now imagine the same message spoken aloud. The form changes, sound instead of ink, but the information remains. In both cases, the information is not separate from the physical system, it is expressed through it. In the quantum world, this idea goes even deeper, because the state of a system, the way it exists, is itself a form of information. And this information is not always fixed. It can exist in multiple possibilities, much like the superposition we explored earlier. But even more intriguingly, it can also undergo transitions, changes that resemble the way matter shifts from one state to another. To make this more intuitive, think again of water. At one temperature it is ice, structured and rigid. At another it becomes liquid, flowing and adaptable. At another, it becomes vapor, spreading freely. The substance is the same, but the pattern of its organization changes. In a similar way, quantum systems can experience what are sometimes called information phase transitions. Not a change in the material itself, but a change in how information is distributed, how it is shared, how it is structured within the system. One of the key elements in this process is something we have already encountered: entanglement, the subtle connection between parts of a system where their properties are linked. In some situations, entanglement spreads widely, connecting many parts of a system together. Information becomes shared, distributed, woven into a larger whole. In other situations, interaction with the environment, what we explored as decoherence, begins to limit that connection. information becomes more localized, more defined, less spread out. And between these two tendencies, there can be a kind of balance point, a threshold, where the nature of the system changes, where information shifts from one pattern to another. You might imagine it like a network of lights. In one state, each light glows independently. In another, they become synchronized, turning on and off together, forming patterns across the network. The system is the same, but the way information flows through it, the way it is organized, has changed. And this change can have profound effects, because in the quantum world, how information is structured determines how a system behaves. It shapes what outcomes are possible. It influences how systems interact, how they evolve over time. This leads to a quietly powerful idea. That information may not just describe reality, but help create it. Not in a mystical sense, but in a structural one. The patterns of information define the possibilities. They shape the landscape within which events unfold. Some physicists have even suggested that at the deepest level, matter and energy themselves may emerge from more fundamental informational processes, that what we experience as physical reality may be the expression of underlying patterns, organizing themselves in consistent ways. You might think of it like a piece of music, the notes, the rhythm, the structure. These are patterns of information. When played through an instrument, they become sound. But the music itself, the essence of it, is not the instrument, it is the pattern. In a similar way, reality may be shaped by patterns that exist beneath the physical forms we observe, patterns that determine how particles behave, how systems evolve, how complexity arises. And as we begin to understand these patterns more deeply, we also begin to see new possibilities. Because if information can change state, if it can be structured in different ways, then perhaps it can be shaped, guided, used in ways we are only beginning to explore. This is one of the ideas that underlies the development of quantum technologies, not just working with matter, but working with information at its most fundamental level, harnessing the way it flows, the way it connects, the way it transforms. There is something quietly profound in this, that beneath everything we see, there may be a deeper layer of patterns, subtle, dynamic, endlessly expressive, and that by understanding these patterns, we are not just learning about the world, we are learning about the structure of reality itself, as this idea gently settles, not as something to fully define, but as something to quietly consider. Another question begins to form. If information is so fundamental, if it shapes the behavior of systems at the deepest level, then what happens when we begin to use it directly? When we design systems that do not just process information in the classical way, but operate within this quantum landscape of possibilities. And it is there, in this transition, from understanding to application, that our journey continues. When we begin to see that information itself may be part of the deep structure of reality, something quietly remarkable comes into view. If information can exist in multiple possibilities, if it can be shared, shaped, and transformed in subtle ways, then perhaps we can do more than simply observe it. Perhaps we can learn to work with it, to build systems that do not just follow the familiar rules of certainty, but instead operate within this softer landscape of possibility. And this is where we arrive, gently, at one of the most fascinating developments in modern science, quantum computing. To understand what makes this so unusual, it helps to begin with something familiar, a classical computer, the device you use every day, whether it is a phone, a laptop, or something else. At its core, a classical computer works with very simple units of information. These units are often called bits, and each bit can exist in one of two states. You might imagine it like a small switch. It is either off or on, 0 or 1. Every image you see, every sound you hear, every message you send is built from vast numbers of these tiny switches, turning on and off in precise patterns. Now, imagine a different kind of system. Instead of being limited to just one state at a time, it can exist in a gentle blend of both, not off, not on, but somewhere in between, holding both possibilities at once. This is what we call a quantum bit, or more softly, a quantum unit of information, often referred to as a qubit. You can think of it like a dimmer switch rather than a simple on-off switch. Instead of being fixed in one position, it can exist across a range of possibilities. And just as we explored earlier, this is not because we do not know its state. It is because the system itself holds multiple possibilities at once, until interaction brings about a definite outcome. Now here's where things begin to unfold in a remarkable way. When you combine multiple classical bits, each one still exists in a single state. 3 bits, for example, can represent one specific pattern at a time, but with quantum bits, the situation is different. If you have several qubits working together, the system can hold many patterns simultaneously, not switching between them, but gently exploring them all at once. You might imagine it like walking through a maze. A classical computer explores one path at a time. If it reaches a dead end, it turns back and tries another, step by step, path by path. But a quantum system behaves differently. It is as if it can explore many paths at once, spreading out, considering multiple possibilities simultaneously, and gradually finding its way toward the most likely solutions. This does not mean it instantly solves every problem, and it does not replace classical computing, but for certain types of tasks, it offers a completely new way of working, a way that aligns with the deeper structure of quantum reality. Now, to keep this gentle and intuitive, we can avoid thinking in terms of complex equations or abstract spaces. Instead, it is enough to hold on to this image, a system that does not commit too early to a single path, but instead allows many possibilities to unfold together before gently settling into an outcome. This ability becomes especially powerful when dealing with problems that involve many interacting parts. For example, consider the behavior of molecules. Even a small molecule can have an enormous number of possible configurations. The way its atoms arrange themselves, the way they interact, the way energy flows through the system. All of this creates a landscape of possibilities that is difficult to explore using classical methods. But a quantum system, because it operates within the same kind of rules, can represent and explore these possibilities more naturally. This is why one of the most promising applications of quantum computing lies in areas like chemistry and medicine. Scientists can use these systems to simulate how molecules behave, to understand how new drugs might interact with the body, to explore materials that could store energy more efficiently, or conduct electricity in new ways. Instead of relying solely on trial and error, they can begin to model these interactions at a deeper level. Not perfectly, not completely, but in ways that were not previously possible. There is something quietly elegant in this, that by learning to work with the principles of the quantum world, we are not forcing nature into our models, but aligning our tools with the way nature already behaves. It is like learning a new language. At first, it feels unfamiliar. The grammar is different, the structure is new, but over time, you begin to see that it allows you to express ideas that were difficult to capture before. Quantum computing is something like that. a new way of processing information, one that reflects the deeper patterns of reality. Now, it is important to keep this grounded. These systems are still developing. They are delicate. They require careful conditions, isolation, stability. Because as we explored earlier, interaction with the environment can quickly blur their quantum behavior. But even in their early stages, they are already revealing new possibilities, new ways of thinking, new ways of approaching problems, and as this idea gently settles, that we are beginning to build machines that do not simply compute, but explore possibilities. Another question begins to form. If information can be shared across space through entanglement, if systems can be connected in subtle ways, then what happens when we use these principles not just for computation, but for communication? Can we send information in a way that reflects this deep connection, where the very act of interference becomes visible, and it is there, in that quiet extension, that our journey continues? As this idea gently settles, that we are beginning to build systems which explore many possibilities at once, it leads naturally to another question. If quantum systems can share information internally, if their states can be connected in subtle ways, can the connection extend outward? Can we use these same principles, not just to compute, but to communicate, to send information, not through conventional signals alone, but through the deeper patterns of the quantum world itself? In everyday communication, information is carried through physical signals. A message travels through a wire or through the air as a sequence of changes. These signals can be intercepted, copied, altered. Even with encryption, mathematical techniques that protect information, there is always, in principle, the possibility that someone with enough time or computational power might find a way to decode the message. But the quantum world offers a different kind of protection, not based on complexity, but based on the behavior of reality itself. To explore this gently, imagine sending a message written in very delicate ink. So delicate that the slightest touch, the faintest disturbance, changes the message immediately. If someone tries to read it without permission, the act of reading leaves a trace. The message itself reveals that it has been disturbed. Quantum communication works in a similar way. Instead of encoding information in stable, classical signals, it uses quantum states, those delicate patterns of possibility we've been exploring. And because quantum states are sensitive to interaction, any attempt to observe or intercept them changes them. This is not a limitation. It is a feature, a built-in form of security. One of the most well-known approaches to this idea is something called quantum key distribution. Rather than sending the message itself through a quantum channel, two parties, often described simply as a sender and a receiver, use quantum states to establish a shared secret key. You might think of this key as a pattern, known only to them, used to encode and decode messages. The key itself is created through the exchange of quantum signals, and here is where the unique property emerges. If a third party attempts to intercept these signals, even in a very subtle way, the quantum states are disturbed, and this disturbance can be detected. It is as if the communication channel carries its own form of awareness, quietly revealing whether it has been touched. Now, it is important to keep this grounded. Quantum communication does not allow messages to travel faster than light. It does not bypass the fundamental limits of physics, but what it does offer is something equally profound. A way to ensure that communication is secure, not through secrecy alone, but through the laws of nature themselves. And this is not just a theoretical idea. Experiments have already demonstrated quantum communication over large distances. In some cases, Particles of light have been sent between ground stations and satellites across hundreds, even thousands of kilometers. These particles carry quantum states that can be used to establish secure keys, linking distant locations with remarkable precision. You might imagine it like two distant points, connected not by a visible thread, but by a shared pattern, a subtle coordination that ensures consistency. And if that pattern is disturbed, both sides immediately know. There is something quietly elegant about this, that security, something we often think of as a human invention, can be grounded in the structure of reality itself, not enforced, but inherent. Now, entanglement, the connection we explored earlier, also plays a role in these systems. In some approaches, pairs of entangled particles are distributed between two locations because their properties are linked. Measuring one provides information about the other, again, not through a signal travelling between them in that moment, but through a shared origin, a unified description. This allows for correlations that can be used to verify the integrity of a communication channel. If the expected patterns are disturbed, it suggests that something has interfered. You might think of it like two copies of a delicate pattern. If both copies remain consistent, you can trust that nothing has altered them. But if even a small discrepancy appears, it signals that something has changed. And in the quantum world, even the smallest interaction leaves a trace. This sensitivity, which can make quantum systems difficult to control, becomes an advantage in communication, a way of detecting interference with extraordinary precision. There are also broader implications. As quantum communication technologies continue to develop, they may form the foundation of what is sometimes called a quantum network, a system where information is shared, not just through classical signals, but through coordinated quantum states. Such networks could support new forms of communication, new ways of linking distant systems, new possibilities for secure data exchange. And yet, even as these technologies advance, they remain connected to the deeper ideas we've been exploring: superposition, entanglement, decoherence. All of these principles working together, shaping how information moves and transforms. There is something quietly reassuring in this, that the same delicate behaviours we have been observing, the same subtle patterns of possibility, can be harnessed, not just for understanding, but for practical use. As this idea settles, that communication itself can be guided by the structure of the quantum world. Another thought begins to emerge. If we can use these principles to protect information, if we can detect even the faintest disturbance, then perhaps we can also use them to sense things that are otherwise invisible. Tiny changes, subtle shifts, signals too faint to detect with ordinary tools. And it is there, in this quiet extension, that the next part of our journey unfolds. And as this idea settles more gently into place, that information can be protected by the very structure of reality. It quietly opens the door to another possibility. Not just sending information, but sensing the world in ways that were once beyond reach. Because if quantum systems are so sensitive, if even the smallest interaction leaves a trace, then perhaps that sensitivity can be used, not as a limitation, but as a tool, a way of listening, very carefully, to the faintest signals the universe has to offer. In everyday life, our senses are limited. We see within a narrow range of light. We hear within a limited band of sound. We feel only what is large enough to touch us directly, and even our most advanced instruments, while powerful, have boundaries. They detect changes, but only above certain thresholds. But the quantum world, with its delicate structure, offers a different kind of sensitivity. To explore this gently, imagine standing in a quiet forest at night. At first, you notice only the obvious sounds, the wind, perhaps distant movement. But as you become still, as you listen more carefully, subtler details begin to emerge. A faint rustle of leaves, a distant echo, a barely audible shift in the air. The quieter the environment and the more attentive you're listening, the more you begin to perceive. Quantum sensors work in a similar way. They are designed to be extremely sensitive to small changes, to tiny shifts in energy, motion, or fields, not because they are large or powerful, but because they operate within that delicate quantum regime, where even the smallest disturbance matters. One of the most remarkable applications of this sensitivity is in the measurement of gravity. Gravity in everyday experience feels constant. It holds you to the ground, keeps objects in place, shapes the motion of planets and stars. But in reality, gravity is not perfectly uniform. It varies, ever so slightly, depending on the distribution of mass around you. Mountains, underground structures, even subtle changes in density beneath the surface, all influence the local gravitational field. These variations are incredibly small, far too small to notice directly, but quantum sensors can detect them by observing how tiny quantum systems respond to gravitational influence. Scientists can map these subtle differences. It is as if the Earth itself, with all its hidden structures, can be gently revealed, not by digging, but by listening to how gravity shifts. This has practical uses: exploring underground resources, studying geological formations, monitoring changes in the environment. But beyond that, it offers something more, a way of perceiving the world, not through direct contact, but through the quiet influence of invisible forces. Another extraordinary application lies in the measurement of time. Time, as we experience it, feels smooth and continuous, a steady flow, moving from moment to moment. But at deeper levels, time can be measured with astonishing precision. There are devices, often described simply as extremely precise clocks, that use quantum transitions within atoms to keep time. Rather than relying on mechanical motion or even electronic oscillations, these clocks are based on the natural rhythms of atomic systems, tiny consistent processes unfolding with remarkable regularity. And because these processes are governed by quantum behavior, they can be incredibly stable, so stable that even the smallest difference in gravitational influence or altitude can affect the passage of time they measure. For example, if you were to place one of these clocks slightly higher than another, just a small difference in height, the clock at the higher position would experience time passing just a little differently, not in a way you could notice directly, but in a way that can be measured. This is not science fiction. It is a subtle consequence of how gravity influences time, something predicted by relativity and now measured with quantum precision. You might imagine it like two melodies playing at nearly the same tempo. At first, they seem perfectly synchronized, but over time, a tiny difference becomes noticeable. One drifts slightly ahead, the other slightly behind. In a similar way, these clocks reveal that time itself, while smooth in our experience, carries subtle variations, shaped by the structure of space and gravity. There are also quantum sensors designed to detect motion, rotation, and even faint magnetic fields. These devices can measure changes so small they would otherwise remain hidden. It is as if they allow us to hear the quietest whispers of the universe, signals that are always present, but usually too subtle to perceive. And what makes all of this possible is the same sensitivity we have been exploring throughout this journey, the same delicate nature of quantum systems, the same responsiveness to interaction, the same subtle interplay between stability and change. There is something quietly poetic in this, that the very features which make quantum systems seem fragile are the same features that make them powerful tools for observation, a kind of sensitivity that transforms limitation into capability. As we learn to work with these systems, to isolate them, to guide them, to interpret their responses, we begin to extend our perception, to see not just with our eyes, but with instruments that reveal deeper layers of reality. And as this idea settles, that we are beginning to sense the invisible, another realization begins to form. If quantum effects can help us detect subtle features of the world, if they can reveal hidden patterns in matter, energy, and time, then perhaps these effects are not just tools we have recently discovered. Perhaps they have been present and used long before we understood them. Perhaps nature itself, in its quiet way, has already learned how to work with these principles, and it is there, in the gentle unfolding of life itself, that our journey continues. When we begin to notice this, we realize that we have learned to build instruments that can sense the faintest signals, measure time with remarkable precision, and work with the delicate patterns of the quantum world. It invites a softer, almost humbling thought. What if we were not the first to learn these principles? What if nature, long before us, had already found ways to use them, not through conscious design, not through deliberate understanding, but through the slow, patient process of evolution, a process that explores possibilities, tests variations, and gently selects what works best. To begin exploring this, let's turn to something very familiar, a leaf, simple, quiet, easily overlooked. And yet within that leaf, something remarkable is happening. When sunlight reaches it, energy from that light is captured and guided through a series of processes, eventually helping to create the chemical energy that supports life. This process is often described simply as photosynthesis, but beneath that simplicity, there is a deeper layer of efficiency. The energy from light does not move randomly through the leaf. It follows paths, searching for the most effective route. And what scientists have observed is that, at very small scales, this energy may explore multiple paths at once. In a way that resembles the superposition we have been discussing, you might imagine it like standing at the entrance to a forest, with many possible trails leading inward. Instead of choosing one path at random, or trying each one step by step, it is as if the system gently samples many paths at once, and naturally settles on the most efficient route, not through intention, but through the structure of the process itself. This allows energy to move with remarkable efficiency, minimizing loss, maximizing output. And this efficiency is not something imposed from outside. It has emerged over time as part of the natural evolution of life. There is something quietly beautiful in that the same principles we are only beginning to understand may already be woven into the functioning of living systems. Another example comes from something even more subtle, the ability of certain birds to navigate across vast distances. Some species travel thousands of kilometers, returning to the same locations year after year, guided in part by the Earth's magnetic field. Now, the magnetic field itself is extremely weak, far too weak to be detected directly by our senses. And yet, within these birds, there appear to be mechanisms that respond to this field, allowing them to orient themselves during flight. One of the ideas explored by scientists is that this sensitivity may involve tiny quantum processes within specialized molecules. These processes could allow the system to respond to subtle changes in the magnetic environment. influencing how signals are processed within the bird's sensory system, not as a conscious awareness of magnetism, but as a gentle influence, shaping perception in a way that supports navigation. You might imagine it like a faint pattern of light, barely visible, guiding movement without ever being clearly seen. Again, this is not about intention. It is not about the bird using quantum physics in a deliberate sense. It's about the structure of the system, allowing it to respond to subtle features of the environment, a kind of natural sensitivity, refined over time. There is also another example, one that occurs within the chemistry of life itself, inside your body and within all living organisms. Countless reactions are taking place. Molecules interact, bonds form and break, energy is transferred, structures are built and maintained. In some of these reactions, particles must move through very small energy barriers. In classical terms, this would require a certain amount of energy, enough to climb over the barrier. But in the quantum world, there is another possibility. A particle can sometimes pass through the barrier without going over it, not by breaking the rules, but by following the deeper structure of quantum behavior. This process is often described as tunneling. You might imagine it like a hill separating two valleys. In everyday experience, to move from one side to the other, you must climb up and then descend. But in this quantum picture, there is a small chance that the system appears on the other side without taking that path, not in a way that violates causality, but in a way that reflects the spread of possibilities we explored earlier. In biological systems, this kind of process can help reactions occur more efficiently, especially when precise energy conditions are required. Again, not through conscious control, but through the natural structure of the system, through the way it has evolved to take advantage of these subtle behaviors. And as we look at these examples together, a gentle pattern begins to emerge. Nature does not understand quantum physics in the way we do. It does not write equations or build theories, but through countless small steps, through variation and selection, it has found ways to operate within the possibilities that the quantum world provides. Not perfectly, not universally, but in specific contexts where these effects offer an advantage. There is something quietly humbling in this realization that the boundary between physics and biology, between the fundamental rules of nature and the living systems that arise from them, is not as sharp as it might seem. Life is not separate from physics, it is an expression of it, a continuation of the same processes, unfolding at a different level of organization. And as this idea gently settles, another question begins to take shape. If living systems can, in their own quiet way, make use of these subtle quantum effects, if energy can flow efficiently, if perception can be influenced by delicate interactions, if reactions can be guided by deeper patterns, then what about something even more subtle? What about awareness itself? The experience of being present, of perceiving, of thinking. Is it entirely separate from these processes, or might it, in some distant and subtle way, be connected to them? Not as a simple answer, not as a conclusion, but as a question, gently opening, inviting us to look a little deeper. And it is there, at that quiet edge, that our journey continues. As this quiet question begins to take shape, not as something to solve immediately, but as something to gently sit with, it draws us toward one of the most subtle and often misunderstood aspects of the quantum world. Not about particles, not about energy, but about the moment when possibilities become something definite. Earlier, we explored how quantum systems can exist in multiple possibilities at once, a kind of gentle openness, where different outcomes coexist, not yet resolved. And we also saw that when interaction occurs, when the system becomes connected with something else, those possibilities narrow, and a specific outcome appears. But this raises a deeper question. What exactly counts as that interaction? Is it simply any physical contact, or is there something special about observation? In everyday language, we often say that something becomes real when it is observed, that before we look, it is somehow undefined. But in physics, the idea is more careful, more subtle. It is not about awareness in the human sense, it is about interaction. When a quantum system becomes linked with its environment, when information about its state spreads, when it leaves a trace that can, in principle, be detected, that is when its possibilities begin to settle into a definite outcome. You might imagine it like a soft image, gradually coming into focus. At first it is blurred, containing many possible shapes, but as it interacts with light, as information about it spreads, the image sharpens, not because someone is watching, but because it is becoming part of a larger shared system. This helps us move away from a common misunderstanding, that consciousness itself directly creates reality. Instead, what we see is that interaction, any interaction, is enough to shape outcomes. The world is not waiting for a human observer. It is constantly interacting with itself, continuously forming definite states through these connections. And yet, even with this understanding, something remains quietly mysterious. Because in certain experiments, the timing and nature of interaction seem to matter in unexpected ways. One example is often described in terms of delayed choice. Without going into technical detail, the essence is this. A system is allowed to evolve, to behave in a way that reflects multiple possibilities, and only later, a choice is made about how to measure it, a choice that seems to influence how we interpret what happened earlier. Now, it is important to approach this gently. This does not mean that the future is changing the past. It does not imply time travel or dramatic reversals of cause and effect. Rather, it suggests that the relationship between events, the way we connect causes and outcomes, may be more subtle than our everyday intuition suggests. You might imagine reading a story where the meaning of an earlier chapter becomes clearer only after you reach the ending. The events themselves have not changed, but your understanding of them has. In a similar way, quantum experiments sometimes reveal that what we observe depends on the context of the entire process, not just a single moment in time. There is also a related idea, sometimes referred to as retrocausality. But again, it is best to approach this softly, not as something dramatic, but as a gentle suggestion that the structure of time at very small scales may not be as straightforward as we experience it, that cause and effect, while still present, may be part of a broader pattern, where relationships extend across moments in ways we are only beginning to understand. What remains consistent across all of these interpretations is a central idea, that reality, at its deepest level, is not simply a fixed sequence of events unfolding independently of interaction. Instead, it is shaped continuously by the relationships between systems, by how they connect, how they exchange information, how they become part of a shared description. This does not make reality unstable. It does not make it subjective in a chaotic sense. Rather, it reveals a kind of participation, not necessarily by conscious observers, but by everything that interacts, a kind of ongoing process where possibilities become outcomes through connection. There is something quietly grounding in this, that the world is not waiting for us to define it. but that we are part of the network of interactions that shape how it unfolds. Your presence, your actions, your measurements, all become part of that larger system, not separate from it, but woven into it. And yet, even with all of this, there is still no single, universally accepted interpretation of how this process works at the deepest level. Different approaches offer different perspectives. Some emphasize the role of information, others focus on branching possibilities. Still others explore more subtle relationships between time and interaction. Each offers insight, but none provides a final, complete answer. And perhaps that is part of what makes this subject so compelling. Not that it gives us certainty, but that it invites us to explore, to reflect, to remain open to deeper understanding. As this idea gently settles, not as a conclusion, but as a quiet shift in perspective, another thought begins to form. If reality is shaped through interaction, if it is, in some sense, participatory, then what does that mean for how we understand our place within it? Are we simply observers, looking at a fixed world, or are we, in some subtle way, part of the process through which reality takes shape? And it is there, in that quiet reflection, that our journey comes to its final step. As this reflection gently settles into place, we begin to sense that reality may not be entirely fixed, but something that unfolds through interaction, through connection, through relationships that extend beyond what we immediately see. It invites one final, gentle perspective, not as an answer, but as a way of holding everything we have explored together. Throughout this journey, we have moved from the very small to the very large, from particles and light to systems and structures, to life itself, and finally to awareness. And along the way, a pattern has quietly emerged, not a rigid rule, but a recurring theme that at every level, reality is shaped not just by individual things, but by the relationships between them, by how they connect, how they influence one another, how they share information. In the quantum world, we saw this through superposition, where multiple possibilities coexist, through entanglement, where distant systems remain connected, through decoherence, where interaction shapes what becomes stable, and through the idea that information itself may play a foundational role. In the world of technology, we saw how these principles can be harnessed to compute, to communicate, to sense the faintest signals. In the world of life, we saw how these same patterns may quietly support processes that are efficient, adaptive, and deeply integrated with the environment. And in our exploration of observation, we saw that reality becomes definite not in isolation, but through interaction, through participation, in the broadest sense. This does not mean that reality depends on human awareness in a direct or controlling way. It does not suggest that the universe waits for us to define it, but it does suggest something more subtle, that the universe is not made of isolated pieces, but of systems in relationship, that what we experience as reality emerges from these relationships, from the continuous exchange of information, from the ongoing interaction between parts. You might imagine it like a vast network, not static, not fixed, but constantly evolving, each part influencing others, each interaction contributing to the whole. And within that network, everything that exists participates, not as a separate observer, but as a part of the system itself. In this sense, the idea of a participatory universe begins to take shape, not as a mystical claim, but as a reflection of how interaction defines outcomes, how connection shapes reality, how nothing exists entirely on its own. Now it is important to hold this idea gently, because it is easy to stretch it too far, to turn it into something more definite than it truly is. Science, at its best, does not offer final answers in this area. It offers frameworks, models, ways of understanding patterns, and while these patterns suggest deep connections, they do not yet provide a complete explanation of how everything fits together, especially when it comes to something as subtle as consciousness. We do not yet know, in a full and detailed way, how awareness arises. We do not know whether it is connected to quantum processes, or whether it emerges entirely from larger-scale interactions in the brain. There are ideas, hypotheses, ongoing research, but no single, definitive answer, and that is perfectly all right. Because what matters here is not reaching a final conclusion, but recognizing the direction in which these ideas point, toward a universe that is not fragmented, but connected, not rigid, but dynamic, not isolated, but relational. You might think of it like a piece of music. Each note exists, each instrument plays its part, but the meaning of the music does not come from any single element. It emerges from the harmony, from the way the parts come together, from the relationships between them. In a similar way, reality may be less like a collection of separate objects, and more like an unfolding composition, a pattern of interactions, continuously shaping what exists. And within that composition, you're not outside the music, you are part of it, not separate from reality, but participating in it, simply by existing, by interacting, by being present. Every breath you take, every thought you have, every moment you experience, is part of that ongoing process, not controlling it, not defining it completely, but contributing to it in your own quiet way. And as this idea gently settles, there is no need to push it further, no need to resolve every question, or to hold on to every detail. It is enough to rest with the sense of connection, the sense that beneath the surface of everyday experience, there is a deeper layer, subtle, intricate, and quietly beautiful, a layer where possibilities unfold, where patterns emerge, where reality takes shape through interaction. And now, as we come to the end of this journey, you can simply let these ideas soften, let them drift, like thoughts at the edge of sleep. There is nothing to solve, nothing to hold tightly, only a quiet awareness that the world you experience is part of something deeper, and that you, in your own gentle way, are part of it too. And so, we've reached the end of tonight's exploration. Whether your eyes are still open, or you're already drifting somewhere between waking and dreaming, thank you for being here, for taking this quiet journey through the hidden layers of reality. If you'd like to return for more gentle explorations, you're always welcome. Until then, let the mind rest, let the thoughts soften, and allow yourself to drift peacefully into sleep.